everyone, this is module 24 of the course on econometric modeling. Module 24 begins the next part, which is part 5, which deals with univariate time series modeling. So, univariate time series modeling, what do they mean, probably would be clearer in later modules, but module 24 to begin with deals with serial correlation. Serial correlation was one of the assumptions under CLRM. So, first of all, continuing with our multiple regression analysis, then inferences, we had earlier talked about heteroscedasticity, which is actually one violation of the CLRM assumptions or Gauss-Markov assumptions. Similarly, we also assume under Gauss-Markov theorem that there is no serial correlation between the error variances or the population errors rather, sorry, not error variances. And now we will first explore that what happens if that assumption is actually violated. So, this module and the next module is on the problem of serial correlation. Serial correlation is also called autocorrelation. The CLRM, that is classical linear regression model, assumes that the random error components are independent from one observation to the next. However, this assumption is often not appropriate for business and economic data. When the error terms are positively correlated over time, they are called autocorrelated or serially correlated error. So, this actually has reference to the assumption of expected value of ui uj equals to 0, that could be conditional upon the values of x for all I j, for all I not equal to j, right. Now, this when this assumption is not fulfilled, we have the problem of serial correlation. We have previously shown that unbiasedness of the estimated parameters can be proved regardless of the degree of serial correlation in the error terms. Alternatively, when we proved unbiasedness of the estimated parameters, we did not need to, or we did not consider whether the errors were serially correlated or not. It did not play any role in that process. Consequences of the error terms being serially correlated include inefficient estimation. So, it has nothing to do with unbiasedness, but it has something to do with efficiency or the estimated parameters being the best parameters. So, inefficient estimation of the regression coefficients, underestimation of the error variance, underestimation of the variance of the regression coefficient, and inaccurate confidence intervals levels. So, whenever we would need error variance and covariance between the error terms, then all those in all those scenarios or situations we will land into trouble if the errors are serially correlated, I am sorry. Before we proceed with the importance and tests of autocorrelation, it is important to introduce the concept of lagged value. The lagged value of a variable, which may be ut, yt or xt, is simply the value that the variable took during a previous period. So, for example, the value of yt lagged one period is written as yt minus 1, and for the purpose of regression they are arranged as shown in this table. So, you can see that this is yt, and if t refers to the current period, then 2008-9 has an observation of 107, 2009-10 has an observation of 102.7. Now, one period lagged value with reference to 2009-10 is 2008-9, or the value associated with 2008-9, which is 107. So, when we are measuring yt minus 1, we are bringing that 107 here. Similarly, this 107 here and so on, right. So, this is the concept of lagged value. In current period, we are considering the value of the previous period of the same variable, and this is how they are stacked. Now, of course, you can see that when we run a regression of y2 on yt1, yt on yt minus 1, then we would miss out on one observation. The first observation is actually dropped from the regression, because for the independent variable we do not have observations pertaining to 2007-8, right. So, if it is actually the total number of observations is t, then for regression I will be able to use only t minus 1 observations, right. Now, we talk about graphical tests for autocorrelation. The two figures on this slide shows positive autocorrelation, where on average if the residuals at time t minus 1 is positive, the residual at time t is also likely to be positive, and similarly if the residuals at time t minus 1 is negative, the residual at time t is also likely to be negative, right. So, you can see that this is here we are measuring ut hat on the vertical axis and ut minus 1 hat on the horizontal axis. So, whenever there is a this is a scatter plot. So, from if we consider this, then we can see that overall whenever this is increasing, this is also increasing, whenever this is decreasing, this is also decreasing, right. So, if we can plot a straight line, upward sloping straight line through this point, then this would generally imply that they are positively related. Now, you can see that we are measuring ut hat on the vertical axis and time on the horizontal axis. So, how ut hat is actually changing or moving across time, and it shows that with time it is increasing, then if it is decreasing, but most often you can see that we are not crossing the horizontal axis very frequently. This implies that if I consider this point, any 2 points, for example this point and this point, then this roughly shows that whenever there was a decline in the compared to this, there has been a decline in the next period, then again there has been a consequent decline. So, whenever there is an upward trend, generally it is followed. Whenever there is a downward trend, that is also generally followed, which implies that overall when the values are decreasing, then they decrease for some period of time. When they start increasing, then again they keep on increasing for some period of time. This itself implies that the current value is positively associated with the previous value and vice versa. Likewise, the following figures show negative autocorrelation between ut and its lagged values. Note that since we do not observe the error terms, autocorrelations are tested using the sample residuals ut hat, since we cannot observe u hat or sorry ut. So, that is why we work with ut hat. Now, you can see that we can plot a downward sloping line through these points, and as a result of which we can conceptualize a negative relationship between ut hat and ut minus 1 hat. You must also observe that all these observations are centered around 0, which implies that even though they are having serial correlation, the error term is actually having mean 0. Now, if the error terms are plotted against time, then this if they are negatively related, then we would first observe that they are changing, they are actually crossing the horizontal axis very frequently, right, because if there is an increase, the next one is a sharp decrease. If the next one is then currently it is a decrease, then the next one is a sharp increase. So, which implies that they are actually not following each other, and as a result of which we have this kind of fluctuations and they are negatively related. Now, we talk about efficiency and inference, that what kind of problem we actually land into if we have serial correlation or autocorrelation. Because the Gauss-Markov theorem requires both homoscedasticity and serially uncorrelated errors, OLS is no longer BLUE or best linear unbiased estimator in the presence of serial correlation. Even more importantly, the usual OLS standard errors and test statistics are not valid even asymptotically. We can see this by computing the variance of the OLS estimator under the first 4 Gauss-Markov assumptions and the AR1 serial correlation model for the error terms. Now, AR1 serial correlation model I am going to define very soon in the next slide itself. Formally, when we assume expected value of ut given xt is equals to 0 and expected value of ut st given or conditional upon the values of x's is 0 for all ts, then there is no serial correlation or autocorrelation, otherwise there is. A particular form of serial correlation is ut equals rho ut minus 1 plus et. Note that specification 1 does not include a constant term because expected value of ut is equals to 0. So, we do not need to include a constant term. This is called an AR1 or autoregressive process of order 1 of the error term. This is AR1 or order 1 because we are considering only one lag. If we would have considered 2 lags, then this would have been AR2. If we would have considered 10 lags, then this would have been AR10, and similarly generalizing by considering p lags, we would have ARP model. We assume the mod value of rho less than 1 because this is required for the stability of the structure, and what it actually implies would be clarified much later towards the almost the last units. Suppose the model is yt equals to xt beta plus ut, the original model. Yes, we also assume that expected value of the error term here is 0 conditional upon the values of the independent variables, that is the previous values of ut, and variance of Et is equals to sigma E square for all t. So, this is homoscedastic and this also has mean 0. So, obviously it follows that it follows a normal distribution with mean 0 and sigma square E as the variance. Now, this is my original model. In module 11 we derived that variance of beta hat is equal to x prime x inverse x prime expected value of u prime x prime x inverse. Now, if expected value of u prime is equal to sigma square in, where in is an identity matrix, then the assumption of sphericality is fulfilled because we have constant error variance and all the covariances between the error terms are 0 and the OLS estimates are blue, right. Also, by incorporating sigma square in here, we can easily prove that we have already done that this becomes sigma square x prime x inverse, which is the usual error which is the usual variance of the estimated parameter, variance of beta hat. Next, we will derive the value of variance of u equals expected value of u prime in the presence of serial correlation. So, errors are generated as this, as it is mentioned that it is an AR1 series. Variance of ut would be variance of this expression. So, say rho being a constant, it comes out, we have rho square variance of ut minus 1 plus variance of Et. Now, variance of Et comes here as sigma E square. Variance of ut, in place of ut here, I again plug in the value of the way I have written ut equals rho ut minus 1 plus Et, ut minus 1 can also be written as rho ut minus 2 plus Et minus 1. So, this expression is actually put in, then what we have is variance of ut minus 1 would be rho square variance of ut minus 2 plus variance of Et minus 1. Now, when I open the bracket and multiply, I have rho raised to the power 4 variance of ut minus 2 plus rho square variance of Et minus 1 is also sigma E square, and we have sigma E square from here. So, in a similar fashion, if I further substitute for the values of ut minus 1 here and then consequently ut minus 3 and so on, then I will have a series like this where sigma E square plus rho square sigma E square plus rho raised to the power 4 sigma E square and so on. By taking sigma E square common, I have 1 plus rho square plus rho raised to the power 4 plus rho raised to the power 6 and so on. This is an infinite GP series. So, we can write it as sigma E square divided by 1 minus rho square. So, this is actually equal to the variance of ut, and since it is not dependent on t, that is the time subscript. So, that would be also the case for variance of ut minus 1, variance of ut minus 2 and so on. So, the variance is constant. The variance of ut minus 1 or ui for all I equals to 1 to t are constant, and that is equal to sigma E square divided by 1 minus rho square. So, what we have is the diagonal terms of the variance covariance matrix are all same, therefore, we have the assumption of homoscedasticity, right. Now, given that ut equals rho ut minus 1 plus Et, we derive the covariance between ut and ut minus 1. So, ut is rho ut minus 1 plus Et and ut minus 1. Rho being constant comes out, we have covariance between ut minus 1, ut minus 1, covariance between Et and ut minus 1. This is basically variance of ut minus 1 and this is supposed to be 0 under the assumption that Et is actually not correlated to the error terms and it has a constant variance. So, this is equals to 0, therefore, we have rho into sigma square E divided by 1 minus rho square as the covariance between ut and ut minus 1. Next is we try to derive the covariance between ut and ut minus 2. Now, again in place of ut I have rho ut minus 1 plus Et and ut minus 2 as it is, right. Again ut minus 2 can be written as I have shown in the previous slide that ut minus 1 would be rho ut minus 2 plus Et minus 1. So, rho ut minus 2 plus Et minus 1 and then Et comes from here and finally Et minus 2. So, what we are having covariance between rho square ut minus 2 rho into Et minus 1 plus Et and ut minus 2. So, rho square covariance ut minus 2 plus rho Et minus 1 ut minus 2 plus covariance between Et and ut minus 2, covariance between Et and ut minus 2. So, what we have again, this is equals to 0, this is equals to 0, we have rho square sigma E square divided by 1 minus rho square. And in a similar fashion, we can prove that when the covariance between ut and ut minus 2, then we have rho raised to the power 2. When it was ut and ut minus 1, we had rho raised to the power 1. Similarly, when it is ut and ut minus j, it will be rho raised to the power j. So, now you can see that the covariance actually depends on the difference between the two time periods, right. So, this is my variance covariance matrix where all the diagonal terms are constant and equal to sigma E square divided by 1 minus rho square. And the covariances are basically the variance term multiplied by rho raised to the power the difference between the two time period. So, this is actually covariance between ut and ut minus 1. So, the time period difference is 1, I have rho raised to the power 1. This will be covariance between ut and u1, the very first period, and that is why this is rho raised to the power t minus 1 and of course, the variance term. So, that is how the entire variance covariance matrix is derived. Since variance of u equals to expected value of u prime is now not equal to sigma square I n, the OLS estimates are not the most efficient one. Now, how do I detect serial correlation or autocorrelation? The most popular or common test is the Durbin-Watson test that was suggested by Durbin and Watson in 1951. DW is a test for first order autocorrelation, that is it tests only for a relationship between an error and its immediate previous value. So, if there is higher order autocorrelation, then that is not detectable by DW test. The test statistic could be interpreted in the context of a regression of the following from. So, this is our AR1 model of the error term where ET is follows a normal distribution with 0 mean and sigma E square variance. The DW statistic has its null and alternative hypothesis as rho is equals to 0 and rho not equals to 0. So, the null hypothesis states that there is no autocorrelation between the error terms. Therefore, under the null, the errors at time t minus 1 and t are independent of one another. If the null is rejected, we will conclude that there is evidence of relationship between successive residuals. DW statistic looks like this. We do not get into the derivation of DW statistic, but then we will certainly get into the implications of the DW statistic. Now, this can also be written as something like this, where you can see that the numerator remains the same, but the denominator is now slightly different, and this is obvious because variance of ut hat is expected value of u t hat square, which is equal to summation t equals 2 to capital T u t square divided by t minus 1. This is basically an unbiased estimator of the population error variance, right. Therefore, we can always write variance of u t hat multiplied by t minus 1, which is the right hand side here, is equal to summation u t hat square, and this is actually the denominator here. We are going to utilize this expression later, and that is why I have mentioned it here. The numerator compares the values of the error at time t minus 1 and t. If there is positive autocorrelation in the errors, the difference in the numerator will be relatively small, right, because one is following the other, one is increasing, the other is also increasing, one is decreasing, the other is also decreasing. So, the difference between the consecutive numbers would be small. While if there is negative autocorrelation with the sign of the error changing very frequently, the numerator will be relatively large. So, if one is coming down, the other one is going up, the one is going up, the other one is coming down, and as a result of which we expect specifically when the signs also change, the difference to be large. No autocorrelation would result in a value for the numerator between small and large. So, for small values we expect positive autocorrelation, for large values of the numerator we expect a negative autocorrelation. But note that the numerator will always be positive because it is actually a squared term. So, the difference could be positive or negative, but it is squared, that is why it is always positive, and then they are summed up over n minus 2 observations. It is also possible to express the DW statistic as an approximate function of the estimated value of rho, which is rho hat, such that DW statistics is approximately equal to 2 minus this expression, and this expression is equivalent to rho. This expression is equivalent to rho hat, the estimated parameter of the AR1 model. So, which is equal to 2 into 1 minus rho hat. To see why this is so, consider the numerator of the DW statistic. So, we consider only the numerator of the DW statistic, which is the original numerator, which is this. And what we observe, we simply expand it like a minus b whole square. So, first of all a square ut hat square, this is b square and then minus 2ab. Now, we consider the first component. This is actually the sum of the observations u t running from 2 to capital T. So, u 2 hat square, u 2, this should be u 3 hat square, then u 4 hat square up to u t hat square. Similarly, when we consider the other term, that is u t minus 1, again t running from 2 to capital T, we are having, this is 2 minus 1. So, it starts from u 1 hat square, u 2 hat square, u 3 hat square up to u t minus 1 hat square. So, you can see that the two sums differ only in terms of the last and the first terms. This is the last term, first term, which is not there in this expression, and this is the last term which is not there in this expression. So, only the last term of the first component and the first term of the second component are not there. So, as t tends to infinity, that is the sample size becomes large and large, the difference between the two sums become negligible. Hence, the numerator of the DW statistic can be written as 2 summation u t hat square. So, we are assuming summation u t hat square and summation u t minus 1 hat square to be approximately equal, right, and that is why we are writing 2 summation u t hat square minus 2 u t hat u t minus 1 hat. Consequently, the DW statistic can be written as 2 minus, we are having this expression in the numerator and in place of this, and in the denominator we have this. So, summation u t hat square and summation u t hat square roughly cancel out with each other. We are left with 2 minus this entire thing on the numerator divided by the usual denominator, right. And this basically is equal to 2 into 1 minus rho hat. Now, why this is so? This is because we note that for the sample residuals the covariance is covariance between ut and ut minus 1 hat is summation ut hat ut minus 1 hat square divided by t minus 1. Now, this is the expression we actually derived here, right. Now, what we are doing is that in place of the numerator we are writing t minus 1 multiplied by covariance ut hat ut minus 1. In place of the denominator we are writing t minus 1 multiplied by variance of ut hat, which I just derived a couple of slides ago. So, t1 minus 1 t minus 1 cancels out and covariance between ut hat and ut minus 1 hat divided by variance of ut hat gives us correlation between ut hat and ut minus 1 hat. So, this is rho hat, and that is how we have 2 into 1 minus rho hat, right. This is approximately equal to the initial expression. Okay. Since rho hat is a correlation, it implies that rho hat would lie between minus 1 and plus 1. The usual correlation coefficients, as they always lie between minus 1 and plus 1. Substituting this limit to calculate dW gives us the following limits for the dW test statistic. So, if rho is equal to 1, I just write for your convenience what we observed is 2 into 1 minus rho hat, right. So, if rho hat is equal to 0, then dW equals to 2. This is the case where there is no autocorrelation in the residual. So, roughly speaking, the null hypothesis will not be rejected, right. So, also rho hat implies no correlation or no autocorrelation. So, rho hat equals to 0 would give us a dW statistic which is equal to 2, and this would correspond to no autocorrelation between the error terms. When rho hat is equal to 1, we have dW statistic equal to 0. So, when there is perfect autocorrelation, perfect positive autocorrelation in the residuals, then the corresponding dW statistic is 0, and when rho hat is equal to minus 1, we have dW statistic equal to 4. This corresponds to the case when there is perfect negative autocorrelation, fine. So, the dW test does not follow, but the dW test does not follow a standard statistical distribution such as TEF or chi-square. dW has two critical values, an upper critical value denoted by du and a lower critical value denoted by dl. We can also write it as d subscript u and d subscript l, and there is also an intermediate region where the null hypothesis of no autocorrelation can neither be rejected nor not rejected. So, the following diagram, this diagram basically shows the rejection, non-rejection and inconclusive regions of the dW statistic. So, 2 is basically where we do not reject the null hypothesis. du to 4 minus du gives us this region. Then if we have 4, rho is equal to dW equals to 4, that is perfect negative correlation, and that is actually valid up to 4 minus the dl lower dW statistic value. So, for this region we reject the null hypothesis. So, we have negative autocorrelation, and for this region 0 to the dW lower limit, we reject again the null hypothesis and it shows positive autocorrelation, with 0 being associated with perfect positive autocorrelation. Now, between du and dl there is region of inconclusion, and similarly between 4 minus dl and 4 minus du again we have inconclusive region. So, if the null hypothesis is rejected and the existence of positive autocorrelation is presumed, if dW is less than the lower critical value, the null hypothesis is rejected and the existence of negative autocorrelation presumed if dW is greater than 4 minus the lower critical value. The null hypothesis is not rejected and no significant residual autocorrelation is presumed if dW is between the upper and 4 minus the upper critical limit. Now, suppose the dW statistic value is 0.86 from a regression of the form yt equals beta 1 plus beta 2. So, we have basically 3 explanatory variables. The relevant critical values for the test are dl at 1.42 and du at 1.57. Therefore, 4 minus du is 2.43, 4 minus dl is 2.58. So, 4 minus du we calculate, 4 minus dl we calculate, we already have values of dl and du. So, du minus dl is 0.15, du minus dl is 0.15. Now, our test statistic says that the value is 0.86. So, the test statistic is clearly lower than the lower critical value. It is lower than the lower critical value because DL is at 1.42. Hence, the null hypothesis of no autocorrelation is rejected and it would be concluded that the residuals from the model appear to be positively correlated. This is a truncated DW statistic model for lower and upper 1% critical values of for Durbin-Watson statistic, and this actually truncated because the observations T is here only up to 40, because the slide can accommodate only up to this many observations. But we can have DW statistics for larger observations as well, and here K prime actually refers to the number of independent variables. So, when we consider DW statistic, the K value actually does not include the intercept term. So, for example, here I have 3 independent variables. So, that we would refer to this column. Consider the DL and DU value corresponding to the number of observations we have, and accordingly we can make a decision depending on the critical or the calculated DW statistic we have obtained. So, these are the references. In the next module also I will continue with the discussion of serial correlation while discussing another test and how to deal with serial correlation, that is how we can correct for the presence of serial correlation, so that my estimated parameters are efficient. Thank you.